Hi, this is Dr. Habib Ahmed, and today I'm going to demonstrate how to introduce beryllium ion implantation in aluminum nitride using Silvaco TCAD. Later, I'm also going to demonstrate aluminum nitride based homojunction diode as well. Aluminum nitride is a wide bandgap material. Its bandgap is approximately 6.2 electron volts, and it's much wider as compared to the contemporary materials such as gallium nitride, gallium oxide, silicon carbide, etc. Also, here is a table listing the comparison of different wide bandgap materials. So, in terms of semiconductor performance parameters, aluminum nitride is either the best or second best as compared to other wide bandgap semiconductors. The critical electric field of aluminum nitride is approximately 1.5 times as compared to that of gallium oxide, 3 times as compared to that of gallium nitride, and 5 times as compared to that of silicon carbide. And because of its larger critical electric field, aluminum nitride has higher Bodiga's figure of merit and higher Johnson's figure of merit as compared to other high power semiconductors. However, until recently, the major limitation in achieving aluminum nitride based high power devices was achieving N and P type doping. There were limitations. People were able to achieve N-type doping up to approximately 1 into 10 to the power of 15 per centimeter cube. And nobody was able to achieve whole concentrations or P-type aluminum nitride films. So, our group at Georgia Institute of Technology, which is Advanced Semiconductor Technology Facility, led by the amazing Professor William Allen Doolittle, was able to achieve both P-type aluminum nitride films and N-type aluminum nitride films. So here is a paper in which we demonstrated P-type aluminum nitride with whole concentrations in the range of 10 to the power of 15 to 10 to the power of 18, mid 10 to the power of 18 per centimeter cube using beryllium doping. Then we have a series of other papers in which we demonstrated aluminum nitride based devices. Like in this paper, we demonstrated N-type doping of aluminum nitride using silicon, and also we demonstrated aluminum nitride based homojunction diodes, as you can see over here from the results. So this has opened the doors for more research on aluminum nitride based high power electronics, and now we can achieve aluminum nitride based high power PIN diodes, and in the future it's going to be a groundbreaking achievement in results in terms of like both research, and also it's going to be applicable in industry. Because of the wide band gap of aluminum nitride, we can basically achieve 3 simple and crucial goals. Like this is for layman understanding as well. A lot of people were asking me, okay, what is your research about? In America, also in Pakistan, what are you doing? What is your research about? So laymen were asking me, and then I had to give it a thought, and then I would tell them that I'm working on a technology which, as compared to the current silicon technology which is dominant, is going to give us 3 major benefits. It's going to be compact in size, and then I would give them examples as well, and it's going to give us higher power, and also it's going to have longer lifetime. So there are definitely a lot of advantages of aluminum nitride technology, and in the near future we will see aluminum nitride based technology dominant in the market. with that preamble, let us now focus on the simulations. So I'm going to demonstrate beryllium ion implantation in aluminum nitride using the Athena module of Silvaco TCAD. We start with meshing. Our structure is running from 0 to 1 micrometers in the x direction initially, and from 0 to 1 micrometer in the y direction as well. And these are spacings at different areas inside the structure. So I actually have the structure over here, and if we look at the dopings, I'm going to plot it later as well, but here, for the sake of understanding of the code, I have to display this primary figure. So here is the figure, and we start with a substrate layer running from 0 to 1 micrometer in the x direction, in the y direction, and from 0 to 1 micrometer in the x direction. And later I mirror it to the right, so then it extend from 1 to 2 micrometers. Here is my p-type region. I introduce beryllium ion implantation in this region, resulting in p-type doping of the aluminum nitride film, and the substrate is basically n-type. So if you talk about the meshing, here is the meshing of the structure. The meshing is denser at the interface and it's sparser in other regions of the structure. Then I define silicon as a donor impurity in aluminum nitride, and I define beryllium as an acceptor impurity for aluminum nitride. I initiate an n-type doping of 1 into 10 to the power of 17 per centimeter cube into aluminum nitride and introduce it as the substrate initially. And then using this block of code, I introduce beryllium ion implantation into aluminum nitride. There is one more critical point over here. Aluminum nitride is not a built-in material in the Athena module of Silvaco TCAD. Like if you go to command process, if you want to deposit aluminum nitride, you're not going to see aluminum nitride in this list. So the way we introduce aluminum nitride primarily is we create the code, we introduce aluminum nitride, and then later, and then we make the structure, and then later we call the same structure, or you can see we import the same structure into the AtLS module of Silvaco TCAD. And you know that aluminum nitride is a built-in material in AtLS. So that is how things work for aluminum nitride. So as I discussed that using this block of code, I introduce beryllium ion implantation into aluminum nitride. And for that, I also seek the help of a couple of other softwares. One of them is SUSPRE, which is used for ion implantation. In SUSPRE, we click on select compound. We choose aluminum nitride. Its density is 3.25 grams per centimeter cube. Then over here I click on that tab and I select beryllium as an impurity in aluminum nitride. I define the energy at 20 kilo electron volts, and I introduce a fluence, or you can also call it dose, of 2 into 10 to the power of 13 per centimeter cube. Here the unit is 10 to the power of 14. So I'm gonna enter 0.2 into 10 to the power of 13 per centimeter cube. Then we are gonna plot it until 2000 angstrom, or you can say 200 nanometers. We click on new, and it gives us the ion implantation curves. This purple curve is the beryllium, I have implanted beryllium inside aluminum nitride, and it gives us certain parameters, like for example its concentration is approximately 0.3 10 to the power of 19 per centimeter cube, or you can say approximately 3 into 10 to the power of 18 per centimeter cube. Similarly, we are more interested in these parameters. The projected range is approximately 746 angstrom, or you can say 74 nanometers, or you can say 0.0746 micrometers. So we need to enter that value into over here into the range parameter 0.076 over here, and it's 746, but actually I am seeking the help from couple of softwares. Like another software is SRIM used for the simulation of ion implantation. So in SRIM, the way we introduce beryllium doping is we select the dopant from here, we enter the energy into this tab, then we define a depth, plotting depth of 2000 angstrom. We choose aluminum, we add another layer, and we choose nitrogen. So now we have aluminum nitride. The density of aluminum nitride is 3.25, so we enter its density, and I want to plot up to like 200 ions. We need to look at different curves, so we check those particular columns. Then we save the input and click on run. So now it has started running the simulation ion by ion. We are going to get up to 200. You can increase the number, but then it's going to take more computation time. We click on ion distribution to see these parameters. Like the ion range over here is 746 angstrom, or 0.074, you can say 0.075 micrometers. So I'm going to enter that value, 0.075 micrometers. Similarly, from SUSPRE, the standard deviation is 323 angstrom, or you can say 32 nanometers. So I enter the value for standard deviation as well, 0.032 micrometers. For skewness and kurtosis, I need to look at SRIM results. So here is the skewness and here is the kurtosis. I already entered these values into my simulation. The results match. So at this point, I'm going to close the SRIM software and also the SUSPRE software. I don't need it anymore. Then we say implant beryllium at a dose of 2 10 to the power of 13, which we already defined here, and at an energy of 20 kilo electron volts. And we already defined the range, standard deviation, skewness and kurtosis for beryllium ion implantation in aluminum nitride. After that, we deposit platinum onto the structure, as you can see over here. This part basically is platinum. If we go to display and we disable the dopings, we can see the platinum part. It's in orange color. And its thickness is 0.1 micrometers. Then we mirror the structure to the right. Like so far we have just created the structure to the left of 1 micrometer. If we mirror it, it's going to extend to 2 micrometers. Then I would define the platinum material as an anode, and I would define the back side of the structure as cathode. Then I save the structure with this name, aluminum nitride underscore beryllium dot str. Str stands for structure. And then I start working Atlas module of Silvaco TCAD. I import the structure already created in Athena. Then I use different models for the simulation of my structure. Impact SELB is a command specifically used for performing the breakdown simulation of different devices. In this code, I'm not going to run the breakdown simulation. I'm not going to run it under reverse bias, but in the upcoming video lecture, I also plan to do that. So for that purpose, I definitely need this Silberher model, which is basically which basically covers impact ionization. Then I want to see different output parameters, for example, the energy band diagrams, mobilities, and current flow lines inside the structure. I'm using the Newton method for numerical simulation of the semiconductor device physics of this homojunction diode. Then I save the structure and I plot the structure under thermal equilibrium. TE over here stands for thermal equilibrium. You don't have to write the TE over here, it's just a name. You can name it anything, but for my own convenience, I've listed TE over here as well. Then in this block of code, I'm actually sweeping the anode voltage from 0 to 7 volts, initially from 0 to 5.5 with a step of 0.25, and then from 5.5 to 7 with a step of 0.05. So that we can smoothly see the turn-on point of the diode. Then I save the structure and finally plot the structure. And later, eventually, I quit the program. So now I've started running the simulation. Here is the structure under thermal equilibrium. I click on display, and with this icon we can look at the meshing. We can also see the doping profiles of the structure by going to net doping, hit apply, click OK. So here is a doping profile of the structure. As you can see that this region over here has N-type doping with a carrier concentration of 10 to the power of 17 per centimeter cube, and then this region actually has P-type doping, which is obvious from this label as well. If you want to see it see more specific values, you can go to Tools, Cut Line, and draw a cut line across the structure. Now here is my doping profile. As this is ion implantation, so this is going to have a certain doping profile, and as you can see over here, the peak carrier concentration is approximately 3 into 10 to the power of 18 per centimeter cube, which we also saw in the SUSPRE software. Then we have 10 to the power of 17 per centimeter cube for the substrate. We can also see the energy band diagram of this structure under thermal equilibrium. EC of T, EV of T, electron QFL and hole QFL, hit apply. So here is the energy band diagram under thermal equilibrium. And here are the IV characteristics. We go to display and we want to look at anode current versus anode voltage. So the band gap of aluminum nitride is 6.2 electron volts, and the turn-on point of the built-in potential of aluminum nitride would be close to that. So the turn-on point is approximately 6 electron volts for this aluminum nitride based homojunction diode. Here is the structure under forward biasing. FB over here stands for forward biasing. So you can go to display, we can see like different contours like the absolute net doping. We can also see the energy band diagram of this structure under forward bias as well, to see the variation in the energy band diagram under biasing. So now here is the energy band diagram of this diode under forward bias, and as you can see that as compared to the thermal equilibrium one over here, under thermal equilibrium we have the same electron and hole quasi-Fermi level, but under forward biasing we have separate electron and hole quasi-Fermi levels. So this was a basic code for introducing beryllium ion implantation into aluminum nitride, and similarly I also demonstrated aluminum nitride based homojunction diode. That's it from me for now. Take care, and I will talk to you next time. Adios.